In the previous section, we talked about Navier-Stokes equations. We derived the Navier-Stokes equations, then we looked at a few exact solutions. We mentioned that there are not many exact solutions that are available. So now we are going to look at solutions that can be for a simplified set of equations called the boundary layer equations. Currently, we'll stick to 2 dimensions. We'll also assume that the density is not changing. And later on, we'll talk about compressible boundary layers towards the end of this course. This material is available as a PowerPoint slide, a PowerPoint and PDF. We're going to be using PDF because some of the equations may not show up properly on the PowerPoint slide. So let me bring the PDF document. We are going to look at some of the concepts that we have looked at before, followed by new topics. We have already talked about molecular viscosity. We said it's a property of the fluid. And in the case of liquids, molecules are closely packed together. Therefore, the electrons in the outer surface of a molecule, outer shells, will be attracted by the protons of the neighboring molecule. Therefore, if one molecule is pulled, the other one will want to follow along. So it's a viscosity occurs in this manner. In the case of gases, molecules are too far apart, so therefore they diffuse from point to point. When they diffuse, they take the mass, momentum, energy information from point A to point B. Think of a sugar at the bottom of a coffee cup in a water, gradually migrates upwards. Eventually the whole cup of water or cup of coffee is sweet as a result. So in the case of liquids, when you heat a liquid, molecules move far apart, the intermolecular forces decrease, therefore viscosity decreases. On the other hand, in the case of gases, when you increase the temperature, this random motion increases, therefore the molecular diffusion also increases. In the previous lecture, we also talked about Stokes relations that link the stress to the strain rate, building upon what Newton had originally found just in one dimension. And when you have a linear relationship between stress and strain rate, we have what we call a Newtonian fluid. Otherwise, you have a non-Newtonian fluid. When we were developing these relationships, there was a quantity called lambda. We found that lambda should be set to minus 2/3 of mu, so that when we define the pressure, whether the fluid is moving or whether the fluid is stationary, the static pressure could be thought of as the average of the pressure over normal forces per unit area on all the 6 faces. We also derived the Navier-Stokes equations, and we found a few exact solutions to Navier-Stokes equations. So these are the equations that we have developed: conservation of mass, U momentum, V momentum. Because we are talking about incompressible flow first, some simplifications can be made. We know that rho is a constant, so it will come out of the picture in this equation. Here rho will come out of this derivative, rho will come out of this derivative, here and also here. What more can we do? You could also do differentiation by part. For example, you could think of rho u squared as rho u times u. So rho u times u is like a p times q. Then p times derivative of q plus q times derivative of p. So you could break this in this manner. Same way, if you think of rho u as p and v as q, then p times derivative of q plus q times derivative of p. When you add it, you get something like this. This right-hand side within the square bracket disappears because of conservation of mass. So the left-hand side was the first two terms on the U momentum equation. So those could be simplified by invoking the conservation of mass. So this goes away, we end up with this. How about the viscous terms on the right-hand side? We have those Stokes relationships. If you plug in tau xx, tau xy, and then assume viscosity is a constant, and also assume the conservation of mass, rho is constant, therefore du dx and dv dy plus dv dy is 0, then we could show that this expression turns into this expression. You need to verify this for yourself so that you can do some minor manipulations of analytical equations in the exam. So as a result of it, our 2D incompressible Navier-Stokes equations look like this: conservation of mass, conservation of U momentum, and conservation of V momentum. Here we have introduced a new quantity called nu, which is our original viscosity, molecular viscosity, which has got an interpretation of what the molecules are doing, divided by rho. We call it a kinematic viscosity because its dimensions are velocity times distance. Velocity and distance are kinematic quantities. It does not have anything like a mass or anything like that, so it's not a kinetic quantity. So nu has got the dimensions of meter square per second or feet square per second. So this is called the kinematic viscosity. So these are the two-dimensional incompressible Navier-Stokes equations that people had wanted to solve. As we talked about, they've been around for a long time, 1845. Now it is 2020, so it's more like 175 years later. We can only solve these equations using CFD. We have software such as Fluent available to you from our VLab at Georgia Tech. If you want to practice some Fluent, you could request a research experience with me perhaps in the fall, and I'll be happy to work with you on that. But the bottom line is you need computational software to solve these equations because they are highly nonlinear. We have unknown times unknown, unknown times unknown, couple. So you have a couple system of nonlinear partial differential equations. So it's a messy problem. Other problem is that you cannot solve a superposition of very simple solutions. You can't add simple solutions and add them together because everything is nonlinear. Therefore, we cannot use some classical techniques that people learn in partial differential equation classes called separation of variables, where each variable is written as a product of a variable in terms of x and y. This does not work for Navier-Stokes equations. So people were kind of stuck right around when these equations appeared, except for a few exact solutions like the Couette flow and Poiseuille flow that we saw. People could not do much beyond that. Another problem was, if you look at the governing equations, they are all second order accurate in space. Second order accurate here, second derivative. So when you have a second derivative, you need two boundary conditions. One maybe at the lower boundary of a lower flat plate, for example in the Couette flow, and the one on the upper boundary, which is the upper flat plate. If it's only a 1D problem, you just need in one direction. But if it's 2D problem, you need the information not only on the bottom and top, but also on the left and right. And in 3 dimensions, you need the boundary conditions for the entire surrounding space. So you need a lot of information to specify the values of U at the boundaries. If you go back to our Couette flow or Poiseuille flow, you would notice that we assume the boundary condition. For example, in the Couette flow, we assumed U equal to 0, U equal to capital V, and then we solve the flow region in this region. So in 3 dimensions, that means when you have a second derivatives both in the x direction and in the y direction and the z direction, you need to solve the entire flow field with the boundary conditions specified at all these boundaries. For example, if you want to know what's going on the nose of an airplane near point A, you can't just solve this small region because these equations are influenced by the boundary condition here. You have to solve for the entire airplane. So which made it very, very messy. In computational fluid dynamics, you will develop a grid over the complete airplane. Then you will solve the Navier-Stokes equations in the entire flow field. So this was the approach, the fact that we have a second derivatives in all the directions produced. So people could not do anything. When you have such a second derivatives in all the three directions, the partial differential equation is called elliptic. You have heard of the word elliptical thinking. That means your thinking is going round and round in circle. So one thought influences the other thought, and then that thought influences the previous thought. There's no logical flow from point A to point B. So here, that's what happens. What's happening in point A will influence point B and point D. In return, what you're specifying in point D will influence point B, which may influence point A. So it's a couple elliptically, everything is coupled to each other. So these partial differential equations are called elliptical equations. There are other type of partial differential equations. If you have a time derivative, it's called a parabolic PDE. Parabolic means you can march in time or in this direction. So in CFD, we will solve this problem by adding a time derivative and forcing it as an unsteady problem. Start with some random initial solution for U, V, and W and pressure. Then keep marching in time until this df dt goes to 0. When things stop changing, then we have recovered the original equation. There are a third set of equations. These appear in supersonic flows. We will see them later. It's called the hypersonic PDEs. So there are classification of three partial differential equations sets. Our Navier-Stokes equations without a time derivative are elliptic. If you have a time derivative, they are parabolic. So engineers were not interested in the solution for the whole flow field. They wanted very, very simple basic knowledge. Is the flow going to separate? Am I going to get a stall over the airfoil? If so, where is it going to happen? Is the flow going to transition from laminar flow to turbulent flow? Because they know laminar flow has got a low drag, turbulent flow has got a high drag. When is it going to take place? Where is it going to take place? They wanted to know what is the skin friction on the surface, so you could integrate it to compute the drag. How much heat is transferred from the fluid to the sauce plate, or from plate back to the fluid. For example, if you have a cold surface, hot gas is flowing over, then the heat will go from the hot gases into the cold plate and vice versa. We also wanted to know how thick is the viscous region surrounding the airfoil. So Prandtl came along in 1904. We will hear about Prandtl quite a few times in this course. He was a German scientist. He came around 59 years after Navier and Stokes. He was an engineer, so he was willing to drop some of the terms in the Navier-Stokes equations as long as it does not sacrifice the physics of the problem. He wanted to retain the physical behavior, but make the equations simpler so that they could be easily solved. So Prandtl did something called an order of magnitude analysis for this purpose. So in this video, we will talk about how he went about doing that for conservation of mass and momentum. His order of magnitude analysis was guided by intuition and also based on experimental observations. He had his own wind tunnel, so he could go and put different bodies such as flat plate or an airfoil. He can watch the flow by injecting smoke. He could stick velocity probes, pressure probes to measure things. So he had a lot of intuitive feel for what the flow fields should look like. So he said, I'm going to show a picture in the next few slides, that the flow region surrounding an airplane or an aerofoil or any body, cylinder, sphere, doesn't matter, you can divide it into two types of flows. One flow is far away from the body, where the flow is inviscid. There's not much viscous effects. And the velocities, if you measure them, they are proportional to or are of the same order as the velocity of the free stream. And the length scales over which changes take place are of the order of the chord length of the aerofoil. So things are changing very, very slowly in the outer region, and there's no viscosity. On the other hand, there is a thin layer near the surface, thin viscous layer, which is called the boundary layer, where the velocity gradually rapidly goes from 0 to close to free stream velocity over a very, very short distance, like a millimeter thickness. So the length may be of the order of meter, but the boundary layer thickness may be of the order of millimeter. So he said we cannot solve the one set of equations for both these regions. We need two sets of equations for these two sets of regions. So in the outer region, far away, the viscosity is neglected and the flow is inviscid. So in our book, chapter 2, chapter 3, chapter 4, chapter 5, all of these are related to inviscid flow equations for the most part. So we are going to get there, but we are now doing viscous flow so that we could apply the knowledge that we learn in the viscous flow towards our vehicle performance. Some of you are taking vehicle performance and you need this knowledge. On the other hand, in the inner region near the surface, less than a millimeter, sometimes 10 millimeter, for an aerofoil that's got a 1 meter long chord, the velocity changes very, very rapidly. So in this inner region, viscosity is very, very important. So here is a picture of a flow. Prandtl was visualizing flows like this. Basically, you inject smoke particles or some tracer particles or a color dye. Inject, in this case, it may be a water tunnel. So follow the track, see what's going on. These are all streamlines. We have talked about streamlines, saying these are lines in space. If you draw a tangent to it, it's going to be parallel to the local velocity. Also, if the streamlines are closely packed, that means you have high velocity. If the streamlines are far apart, we have a low velocity. Rho AV, density times area times velocity, is constant. So if the velocity is small, the area rises and vice versa. On the upper surface, at the low angles of attack, we have a attached flow over most of the surface. That means the flow is following the surface, and you get some kind of a wake behind the body. If you increase the angle of attack, the flow gets separated more and more. If you have an even higher angle of attack, the complete flow is separated, it has stalled. But the bottom line is, if you look at the thickness of the viscous layer in the attached region and thickness of the viscous layer in the attached region, this thickness is very small compared to the length or the chord of the aerofoil. For fully separated flows, this thickness is very large. Therefore, Prandtl's assumption that the viscous layer is thin is no longer valid. So if you have a fully separated flow, you have to go back to Navier-Stokes equations. You have to solve it using CFT. But if you have an attached flow or flow with small amounts of local separation, you can use Prandtl's theory. Therefore, Prandtl's boundary layer hypothesis is that the flow may be divided into two regions. One is an outer region where the flow is inviscid, We are going to apply chapter 3, chapter 4, chapter 5, chapter 11, chapter 12, etc. are all for that particular type of a flow field. But near the body, you have a very, very thin layer where the thickness of the boundary layer, delta, is very, very small compared to the length of the boundary layer from the leading edge to trailing edge. So this is the Prandtl's hypothesis. So he is going to use an order of magnitude analysis. So we are going to briefly start explaining it starting from our next lecture video. So we are going to look at steady flows, no unsteady. Incompressible, that means density is constant. Of course, viscous flow. So we are going to trace the path that Prandtl took in 1904 to simplify the Navier-Stokes equations by throwing away some terms and keeping other terms. What did he do? How did he do that? So that's what we are going to be talking about in the next video.